So we're pleased today to have Gordon Krnjaic. Did I almost get it? Yeah. Krnjaic. Yeah, I shouldn't have given that. And he's going to tell us about a new frontier in the search for dark matter. Let me tell you a little bit about Gordon. So he's an associate scientist at Fermilab. He's also a member of the KICP. Before he was an associate scientist at Fermilab, he was a David Schramm Fellow. And so I did a little research. He got his PhD in 2012 at Johns Hopkins University. And I couldn't find his CV online, so that got me into more searching around. And his PhD advisor was David Kaplan. And then I accidentally got to the family tree thing, which is pretty interesting. And David Kaplan's thesis advisor is Ann Nelson at the University of Washington. And Ann Nelson is also married to David Kaplan, but a different David Kaplan. And then I thought, okay, let's follow back and let's see who the famous people. So Howard Georgi was pretty famous, and Ann's PhD advisor, and then Charlie Sommerfeld. Some of you know Charlie Sommerfeld. And then Julian Schwinger. Oh, that's starting to be really good. And then I. Robbie. And then the whole damn thing explodes because Robbie had 4 PhD advisors, which I really don't understand, but he really was a big personality, including Arnold Sommerfeld, so another Sommerfeld. And then that brings in Sommerfeld, like, supervised everybody, including many people at the University of Chicago. So quite a distinguished family tree. From Hopkins, he went to the Perimeter Institute and then Fermilab. So he's going to tell us about a new frontier in the search for dark matter. And you're guaranteed by the end to understand the following acronyms, and probably more. SHIP. Are you going to do SHIP? Okay, a little bit of SHIP. Daedalus?
No.
Oh, okay. Somebody will have to ask about Daedalus. BDX and BDX. So Gordon, take it away.
All right, well, thanks for the invitation and for the warm welcome, and thanks to everybody for risking life and limb to come out here on this truly beautiful day. And I'd like to tell you a little bit about a new way to think about dark matter and a new way to look for it using fixed target experiments. But before we launch in, I think it's useful to start just by looking at the Mount Rushmore of open questions in fundamental physics and cosmology. And so up here we have all the things that we know are part of nature, but that we don't have any sort of room for in the standard model of particle physics and interactions. So we know that there are neutrino masses because neutrinos oscillate. We know that the universe is made up of more particles than antiparticles. And we have excellent reasons to believe that the universe underwent a phase of inflation at the very earliest times. We also know that the universe is currently accelerating its expansion due to some other substance. Maybe it's a cosmological constant, and maybe it's something more exotic. But what all of these questions have in common, despite being things that we haven't currently answered, is that by and large, they tend to involve theoretical solutions which can be straightforwardly added to the standard model, but yet they involve physics and energy scales that are not very readily accessible to experiment. One of the major exceptions to this is the presence of dark matter. It makes up about 24% of the cosmic pie chart. We have excellent evidence for its existence, and by contrast, unlike all these other problems that live in this laundry list, it's something that could, at least in principle, be right under our noses, and we should be very aware of all the possibilities there are for discovering its non-gravitational interactions. So this is no news to anybody here at KICP, but we have remarkable evidence for the existence of dark matter. We know that rotation curves suggest the presence of about 5 times as much dark matter as there is visible matter based on the motions of stars and galaxies. We know that light is bent by gravitational potentials, and that tells us that there's about 5 times as much dark matter as there is visible matter in lots of different observables. We know that this is on striking display in the collisions of galaxy clusters, where here we're looking at the bullet cluster and colorized hydrogen gas and the gravitational lensing, which is used to map the full potential of this region. But maybe even more impressively, we have early universe and very large-scale observations of the matter power spectrum and the CMB power spectrum, which independently tell us that the universe is filled with about 5 times as much dark matter. And maybe a critical piece of the puzzle here is that we can also ask what the light element yields from Big Bang nucleosynthesis imply for our assessment of the cosmic inventory. And the critical ingredient here is that BBN is a lovely theory that only depends on the barium to photon ratio, and it depends on the expansion rate when the universe was an MeV in temperature. And based on this, and based on the observed element yields, you can work back and figure out what the barium density at the time was, and you can convince yourself that that's the same number that we observe today, which is woefully inadequate to account for all the dark matter that's out there, so it's not baryonic. The big picture here is that we have multiple consistent observations that indicate a compelling picture that there is about 5 times as much dark matter. It's coming from the whole 4 volume of the universe, starting from about 13.7 billion years ago, extending out to the present times, and covers a whopping distance scale from kiloparsec distances on the order of dwarf galaxies, going all the way out to gigaparsec scales. We have evidence coming from surveys and from the cosmic microwave background. But that's largely underdetermining the microscopic properties of dark matter. The holy grail here is to extend our knowledge down to terrestrial scales so that we can understand what its microphysical properties are. And the bad news is that that evidence leaves us largely in the dark. We know that dark matter can't be lighter than about 10 to the minus 20 electron volts, because if it were, then it wouldn't fit inside dwarf galaxies. That would make its Compton wavelength much larger than a kiloparsec, so that's ruled out. We also know that if dark matter is between 10 to the minus 20 eV and about 100 eV, it has to be bosonic, because otherwise, if you try to pack a lot of fermions into something like a galaxy, by the time you fit enough of them in there, by Fermi exclusion, some of them will end up at a Fermi surface where their typical velocities are in excess of the galactic escape velocity, and that's ruled out. So you have to pack a lot of bosons into a galaxy if you're going to have dark matter be that light. And then if dark matter is heavier than the Planck mass, then it better be a composite object. Maybe some sort of exotic dark nucleus, or maybe a primordial black hole. But other than that, the available evidence doesn't really help us narrow it down. There's a huge space of allowed possibilities here, and we'd like to be able to do something about this situation. But if we can't go any further than the available gravitational evidence, it's kind of a hopeless enterprise. We have some 80 orders of magnitude to play with, and it's absolutely essential that we have some theoretical guidance in how to think about narrowing this scope down. And it's important to walk a fine line. If you choose too much theory bias in this, then you'll be limiting yourself and thinking only about, say, WIMPs, or about very specific kinds of dark matter models, and you'll miss the forest for the trees. And on the other hand, if you're too wide open, you don't really know where to start. And so the goal is to find something that's grounded in some physics that we can all agree on, but that doesn't leave the playing field too far open. So with that in mind, I'd like to start by specializing to some theoretical intuition regarding thermal dark matter. And I won't talk about the WIMP miracle, and I won't talk about supersymmetry or any of the usual things that come along for the ride when we talk about thermal dark matter. Once we've got a little familiarity with this, I want to say a few things about what's different about light thermal dark matter, so something that's much below the typical scale of WIMPs. And I'll make a bold claim that we'll be able to launch a program, in principle, which can test all predictive models, and we'll get into the weeds on what it means to be predictive. So let's start with thermal. We can ask, was dark matter ever in thermal equilibrium with the standard model? If the answer is no, then you have to ask, well, how was it populated? And there are 2 trees of possibilities. One is that dark matter started off in some sense as an initial condition, and there's several models in which that's a requirement. So for example, if dark matter is an axion, you have to understand something about what its misalignment angle was in the early universe, or whether the global symmetry that give you the axion was broken before or after inflation took place. Something similar is true with, say, a WIMP-Zilla, where dark matter is some super heavy object that was produced non-thermally, or if dark matter is a primordial black hole and you have to modify the inflationary power spectrum in order to seed the structures that will ultimately form the black holes. And the downside of this tree is that it's rarely predictive. You have to know something about a very high energy scale that we don't currently have any empirical access to in order to say something definitive about anything on this list. The other possibility, if dark matter is not thermal, is that it has some feeble coupling to us. And some examples of this are, say, sterile neutrinos through the so-called Donaldson-Woodrow mechanism, where some small coupling, maybe it's a mixing angle between a sterile and an active neutrino, allows for dark matter which was initially absent in the universe to become populated through some small interaction which never enables thermal equilibrium to take hold. So there are lots of models like this. Friesen is another example, and so-called super WIMPs, which are badly named, are also on this list. And the downside of this tree is that it's very hard to test these, because by design, you have some very weak coupling that prevents you from achieving equilibrium, but then it's harder to ask yourself how to look for this in the laboratory. We could also ask what happens if dark matter does reach thermal equilibrium. That means that at some point, the number density of dark matter particles is comparable to the number density of photons and other things which are in equilibrium. It's set by the temperature, and you can ask some follow-up questions about where that density went. If the answer is nowhere, if the co-moving density stays fixed, so it's only diluted by Hubble expansion, then we have some things to hold on to. Today we know that the dark matter density cosmologically is a certain number, and we know how many CME photons there are, and so if the number densities remain comparable, dark matter has a mass of about 10 electron volts, and that's terrible because it means that that's too hot for the successful formation of large-scale structure, so we have to move on. So the answer can't be that it went nowhere. Maybe the dark matter density went to stable dark sector particles, and then we can break that down and ask whether those particles are light or heavy. If they're light, so dark matter maybe traded some of its number density for dark radiation, then there's a lot of dark radiation in the universe, and you've got some fast talking to do. On the other hand, if dark matter gave its density to heavier particles, then you just shift the problem over to some other particle, which is then too hot to form acceptable structures. And so both of these options require some non-standard cosmological possibilities, which I'm not going to entertain for the rest of this talk. The real interesting possibility is if that huge entropy, which was previously stored in the dark sector, is transferred to visible matter. And there we break it down further. We can transfer that entropy through a cascade of steps where we have hidden annihilation. So dark matter first annihilates into some dark sector particle, which then decays to standard model particles. We'll refer to this as hidden annihilation, and the bad news here is that it's not very predictive, because what you test in the laboratory is how dark sector particles interact with visible matter. So you'd be able to work this last step in reverse, where standard model particles give you the intermediate step, the dark sector particle into which dark matter annihilated, but it doesn't tell you about what you'd really like to know, which is the thing that put dark matter in the universe in the first place. The real interesting case is direct annihilation, and that's the sense in which we'll discuss predictive models. So if dark matter annihilates directly into standard model final states without some intermediate step, that gives us a predictable, testable origin. There's a minimum value of something in the laboratory that you can measure which has to satisfy some inequality in order for dark matter to walk and talk the way that we observe it to. And so that's what I'll specialize to in the rest of the talk. And we're already familiar with the WIMP side of the story, and I'd like to fill in some of our intuition about what it means for this to happen if you're dealing with dark matter below the proton mass. But independently of just how you step through that tree of possibilities, there are lots of great things that equilibrium does for you which are independent of the usual things that we think of in the WIMP miracle. So for example, equilibrium is great because it's generic. You actually have to work kind of hard to avoid thermal equilibrium in the early universe. And as an example, consider some Lagrangian interaction which morally is a lot similar to 4 Fermi theory. You have 2 dark matter particles chi, and you have 2 fermions F in the standard model. And then you ask, at what point does that interaction compete with Hubble expansion in the very early universe? You write down some simple tilde level expression. You could convince yourself that as long as the coupling is greater than about 10 to the minus 8 in these appropriate units, then you're going to reach equilibrium. So if dark matter has interactions that are anything like the kinds of interactions that we've already discovered in the matter that we know and love, equilibrium is a pretty generic consequence. It's worth remembering that even the standard models of neutrinos were in thermal equilibrium at one point. So you'd need things that are way more weakly coupled than even the weak force of the standard model in order to avoid this. There's certainly models which do so, but this is a sort of a random place if you throw a dart in the parameter space. This is what's going to happen. And nearly all of the models that are testable, certainly in any sort of accelerator or direct detection experiment, would feature equilibrium at early times. exciting. The other thing about it is that you have to have a minimum annihilation rate, because you have to have some mechanism by which you take this huge thermal overabundance and then bring it down to an acceptable level to account for the density that we observe today. And that means that we can write down the equilibrium distribution as just some integral over a Fermi-Dirac or Bose-Einstein distribution here in the universe. At high temperatures, this goes like T cubed, and at lower temperatures, it feels Boltzmann suppression. So you start writing this wave all the way down as you annihilate in equilibrium, and then eventually expansion wins out. You've depleted so many of your particles that two annihilation partners can't find each other in a Hubble time, and the dark matter density freezes out. We're all familiar with this in one guise or another. The simplest scenario is one where the population is symmetric and you've got equal numbers of particles and antiparticles, or maybe there's no distinction between particles and antiparticles. Everyone can annihilate everybody. That leaves us with a target that the cross-section has to be about 210 to the minus 26 centimeters cubed per second. And that's a pretty robust statement unless you're changing cosmology in some non-trivial way. So this is a diagram, roughly, of some bars that represent the standard picture. We have some thermal density at early times, and we want to annihilate some portion of this. This is exaggerated for effect. What you'd actually want to do is annihilate almost all of it, some 9 orders of magnitude down. And then you're left over with some equal numbers of particles and antiparticles today. And we normally think of this as being true only in cases where there's a symmetric population of particles and antiparticles, and that's false. Because even if dark matter is sort of like baryons, where there's an asymmetry, you have more particles than you have antiparticles, that issue is actually independent of whether or not you reach thermal equilibrium. If you do have a conserved quantum number that tells you that dark matter is locked into some dark baryon number that you can't change, you'll still have a thermal density on top of that, but this extra stuff is along for the ride, which means you actually now have to annihilate more of the thermal stuff, which is symmetric, in order to achieve the right dark matter density. So even though you might think that this is a scenario that doesn't play by the rules of thermal dark matter, it still secretly does, and there's still secretly a target that you have to satisfy in order to get the right observed density today. It just looks a little different because there's an asymmetric component. And you might say, okay, forget that. What if I have co-annihilation? We're perturbing around the various possibilities. So now, dark matter, which we'll call Chi1 here, has an unstable friend, and we can all relate to that. And this unstable partner particle is a little bit heavier than the dark matter itself. So when they find each other to annihilate, by the time the freeze-out takes place, which is on the order of the, when the temperature is on the order of the dark matter's mass, the heavier friend is a little bit more Boltzmann suppressed than the actual dark matter itself, which means that in order to overcome that mild Boltzmann suppression, you need an even larger cross-section in order to achieve the right relic density, and sometimes it's a much larger cross-section. The key point in all of this is that the usual intuition that we have about particles and antiparticles annihilating each other to achieve the relic density is the smallest that the rate can possibly be. That generally, as you perturb around different possibilities in theory space, you're going to end up with much more stringent requirements. And so if you can figure out a roadmap to get down to the vanilla case, where it's just regular old particle-antiparticle annihilation, and you're sensitive experimentally to the couplings that enable that, then you'll have actually tested a whole broad range of theoretical possibilities with a given experiment. So another thing that we really like about being in thermal equilibrium is that the initial condition is known. I don't have to tell you anything about what was going on during inflation or baryogenesis in order to be able to tell a whole story about what dark matter was doing and how it got here. The masses and couplings are alone sufficient to tell you everything that happened. And the only other possibility that has the same degree of insensitivity to very high energy scales is freezing, where you never actually reach equilibrium, but dark matter is nonetheless produced through small interactions with visible matter. That mechanism, however, relies on some pretty ad hoc assumptions, namely that your initial condition was that the density was 0, independently of what inflation did. And even if you have good reason to think that was realized in the universe, dark matter is still only produced through very tiny couplings, and that makes life much harder. But the most important thing that it does, and this gets us back to the vast playing field of possibilities independently of any sort of thermal guidance, or any sort of theoretical guidance, is that it dramatically reduces the range of possible dark matter masses, independently of any other consideration. We know that if there's thermal equilibrium, dark matter better be heavier than about an MeV, because otherwise freeze-out is taking place at the same time as BBN, and that's very dangerous. On the other hand, dark matter should be heavier, or should be no heavier than about 100 TeV, because then you need a cross-section that's in violation of quantum mechanical unitarity in order to get the magic thermal number for the size of your cross-section. And then if we break that available playing field down into two regions, we'll think about light-dark matter as being below the proton mass, roughly between the electron and proton masses, right under our noses. And then everything that we'll think of as heavier, I'll just call WIMPs and ignore for the rest of the talk. But it's worth noting that we have a lot of powerful searches and a lot of different techniques to go after WIMPs and WIMP-like dark matter. These are extraordinarily effective. That program has spanned some 10 orders of magnitude in sensitivity over the past couple of decades. But unfortunately, it falls quite short when you get right to around the GeV scale. Typical direct detection techniques tend to fail. You don't have enough kinetic energy deposited inside your detector to be observable above experimental thresholds. There are large astrophysical backgrounds for indirect detection, and colliders have large backgrounds for mismeasurements of observable objects. So we really need new techniques to go after light-dark matter. And it's worth noting that we don't actually have any signals coming from this existing search program, so we should be more humble than we can our priors about where we expect dark matter to be. And so I'll focus on the MeV to GeV scale for the rest of this talk. So what's different about being in this mass window? Well, for starters, light-dark matter has to be neutral under the standard model. Now, that's not something that we expect from WIMPs. The W in a WIMP is to be taken seriously. That means that this is a weakly interacting massive particle. It feels the honest-to-God weak force. That doesn't have to be true, and in fact, it can't be true of lighter dark matter because that would have been discovered. If you interact via the weak force, you would have been produced at previous experiments, and you would have been discovered at LEP and at the Tevatron and at UA2 and everything else that was conducted in previous generations. So we know that's not the case. But another less appreciated part of the story is that light-dark matter requires light new force carriers if it's going to be in thermal equilibrium. If you don't have thermal equilibrium and you're trying to do this with just standard model forces, so say GF here is the Fermi constant, if I want my annihilation to take place directly into standard model particles, then you quickly come to appreciate that if dark matter is at the GeV scale, that's a woefully inadequate cross-section. It's way too small. And it only gets worse as you make the mass smaller. So absolutely you need light new forces. So it's not just a story about dark matter, it's a story about dark matter and dark forces, and that should sharpen the focus for what kinds of things we expect to find experimentally. And it's also worth noting, in stepping through some of the possibilities on the table here, is that this annihilation has to proceed through renormalizable interactions. So we can't just write down any old effective interactions like G Fermi in the 4 Fermi theory, because that's an example of something that actually doesn't give us a large enough rate. That if we want to have something which has a shot at giving you thermal freeze-out for a GeV scale particle or lighter, that better come along with another lightning particle. In other words, all the particles are in the spectrum and are energetically accessible if you can make the dark matter. A zeroth order question that we can ask, knowing that we have these light new forces, is who's heavier? Is it the dark matter, or is it the particle which enables the dark matter to interact with us, the mediator? And if the dark matter is heavier, then generically, reading time from left to right, the annihilation process, which sets the abundance, will predominantly be dark matter giving you pairs of mediators. And this is the hidden annihilation scenario that's not predictive. On the other hand, on the right side, if I force dark matter to be lighter than the mediator, then the only kinematically allowed annihilation process is where I treat the mediator particle as a virtual intermediate state, and I put standard model particles in the final state. So I annihilate directly into things that we can see, and that means that the coupling to the standard model plays an essential role in ensuring that we have the right abundance. The consequence of making this choice is that the mediator will then decay predominantly to dark matter particles. Because now the mediator is going to be heavier than the dark matter, and the coupling to the dark matter is generically much, much greater than the coupling to the standard model. So the name of the game here is to look for invisibly decaying particles. That gives us direct access to these predictive scenarios where the coupling to us plays a key role in how dark matter is produced. So we'll emphasize those for the rest of the talk. So now what kind of mediator can we have? We know that it has to be a light new neutral particle, but we know that we have other light neutral particles in the standard model. So the simplest possibility might just be that we mix with one of those. That all particles which have the same quantum numbers can mix with each other. Everything not forbidden is compulsory. And so if, say, I have a light new scalar particle and it carries no charge, and it has CP even properties, then I can mix it with the standard model Higgs boson with some epsilon rescaling. So that this particle inherits all of the Higgs boson's properties. It inherits the fact that it couples predominantly to the masses of particles. The heavier the particle, the more strongly coupled it is. The bad news, though, is that if we're talking about predictive dark matter, where we demand that this coupling is big enough to give us a dark matter that annihilates 2 electrons at the scales that we care about, then that also opens the door to very dangerous processes, because now all of the heavier particles are more strongly coupled to this light new thing that we've added. So for example, if I have a big enough epsilon in order to ensure that I have a sufficient annihilation rate for dark matter, that same epsilon is going to live in Feynman diagrams that enable very dangerous rare decays of, say, kaons. So in this case, if you look at the very well measured properties of the kaon, where it can decay to pions and to neutrinos at a very, very small rate, which has been measured, this would be a huge contribution to that, because this would look exactly the same. You would have a kaon, which is a strange quark inside of a bound state that it then decays to a down quark, and in this process, if we've added this other particle to nature, can also emit the dark matter and this new scalar. And that turns out to be wildly ruled out. So we can already say something about very predictive models that try to invoke scalar forces. They're dead in the water. You can't use them. But you can use all the other ones. And so the other ones that we'll talk about involve mixing either with the standard model photon, so add a new vector particle, an A prime, a dark photon. It has the same quantum numbers as the standard model photon, that it'll have a mass, because we don't want the dark matter to carry a long-range interaction. It can mix with the photon with some epsilon strength, and so there, the same force that talks to us and talks to the dark matter interacts through the electromagnetic current, but with diminished strength. So all of your intuition about charged particles should hold, all of your intuition about photons should hold, except that this thing will be more massive. The other possibility, which is morally very similar, involves a fifth force. So now, instead of having a new particle which just quantum mechanically mixes with the particles that we've already discovered, we can just add a completely new particle and give it direct interactions to standard model fermions. And it turns out there's a very limited list of theoretically consistent possibilities. That the standard model's forces are very delicately organized in such a way as to make very dangerous processes cancel against one another. These are called anomalies. Anomaly cancellation requires that if you add a new force to nature, you better couple it to just the right combination of currents in order for these dangerous things to no longer happen. That limits the scope of possibilities that you have, but the moral of the story is that all of the other possibilities that you could have written down to do this job for you morally are very similar to the dark photon. So I'm just going to specialize to that. So the scenario that we should have in mind from here on out is that dark matter is some particle below the GeV scale, and it couples to something that's like a photon, but that dark photon has a mass. That dark photon can also interact with the standard model in a way that's related to the charges of standard model particles. And once we've got some intuition for that, all of these other ones are very similar. When we're asking what kind of dark matter particles we should have, though, now that we've figured out what kinds of forces are acceptable, it's worth stepping back and noting that there are actually very strong CMB bounds on dark matter annihilation. Now, we might think that because the CMB takes place at temperatures of about an electron volt and lower, that this should have nothing to do with dark matter annihilation, because thermal freeze-out occurs when the temperature is much higher, even for the kinds of things that we're talking about. I could have an MeV scale dark matter particle, and it's in thermal equilibrium, and then it freezes out just below the MeV scale, and then annihilations are no longer efficient at changing its overall number density in the universe. However, that doesn't mean that annihilations actually stop. It just means that they're way out of equilibrium. So they'll still happen rarely with some very small rate. And when they do, they can leave an imprint in the CMB power spectrum. The measurements are good enough that even these rare out-of-equilibrium annihilations that happen at electron volt temperatures can now ionize hydrogen because you're depositing a lot of energy through this annihilation. That means that there's more ionized matter in the universe and that CMB photons experience more attenuation as they pass through it, more than the standard model predicts, and we've already got very strong limits on that. And so what that means is that we are not allowed to have an S-wave cross-section for dark matter below 10 GeV. That's what this plot up here is telling us from the plot collaboration. But what they don't tell us is that this thing is really a cross-section that's evaluated at the time of recombination. So there's some efficiency factor for how often a typical annihilation event will ionize hydrogen. That depends a little bit on what final state it annihilates to. But by and large, if these are all sort of taken to be order 1 or 0.1, which is the case for almost every final state in this category, then if you choose a thermal relic size cross-section at the time of the CMB, then that's ruled out below 10 GeV. But of course, that's a strong assumption. That cross-section doesn't have to have the same value at early times as it does at later times. And there are models where annihilation shuts off completely by the time you get to the CMB, and so we'll see some examples of that. But this is something worth keeping in mind, that any model of dark matter that's safe, that reaches thermal equilibrium, gets its abundance by annihilation, and lives below 10 GeV, better have some cross-section that can be safe from the constraint that this plot implies. And we can write down some representative cases that realize the various possibilities here. So what we'd like to do is take our dark photon, which is the representative force carrier that we've added to talk to the standard model. We're going to couple it to a current of dark matter particles, and here's some representative possibilities for what that can be. So let's go through the first case. Here, dark matter is an asymmetric Dirac particle, sort of like a dark electron. In that case, it's asymmetric, and that does the role of making it safe from CMB bounds, because by the time that you get to the CMB, when the temperature of the universe is in EV, you've already annihilated away all your antiparticles. There's nothing left to deposit energy into the plasma at this time and to ionize the newly formed hydrogen, so you know that that's going to be safe. Similarly, you can imagine that dark matter is a pseudo-Dirac fermion, which is sort of like a Dirac fermion, only you take the vital components inside of the Dirac fermion and you split their masses a little bit by adding a Majorana mass. The details of this aren't so important, but the qualitative difference is that you essentially have two particles in your spectrum, a Chi1 and a Chi2, and they undergo co-annihilation. They have to find each other in order to annihilate. And the heavier of these two is unstable, and so it gets depopulated by the time you reach the CMB. And you could also imagine that the dark matter particle that interacts in this current is either a Majorana particle or a scalar particle, in which case the cross-section for the direct annihilation process will have as its leading component in the non-relativistic expansion a dependence on the velocity squared, which means that at early times, when freeze-out is taking place, this is not a significant penalty, but by the time you've redshifted your way all the way down to the CMB era, this thing is negligible. So safe models require either P-wave annihilation, as in the case of the scalar or Majorana particle, or a different dark matter population by the time that CMB observables take hold. And in both categories, a surprising consequence is that you don't have any serious prospect of conducting any indirect detection searches because there's no annihilation. They're specifically chosen to prevent annihilation during the time of the CMB, and so you certainly don't have any appreciable annihilation at even later times like today. So to put it all together, this is the kind of model that stands in for all the viable models of thermal dark matter below the GeV scale, which are also predictive and allow for direct annihilation into standard model visible particles. We have the dark side of this diagram, where we have a dark fine structure constant labeled with an E. There's some kinetic mixing parameter between a visible photon and a dark photon that measures how strongly this new force couples to standard model particles. And then we have the usual electromagnetic current on the right side of this diagram. The Lagrangian here is essentially identical to QED. It's a doubling of QED of quantum electrodynamics. Only the photon with a prime, the dark photon, now has a mass. It has some diminished coupling to regular charged particles and an undiminished coupling to dark matter. And this is more or less similar to the other possibilities for fifth forces that we could have written down in this place. We could have said that it's, instead of the electromagnetic current, the current that knows the difference between baryon and lepton numbers, or a current that knows about the differences between, say, individual lepton flavors. But these all essentially walk and talk like the same duck. So, now that we have some intuition for what kinds of dark matter scenarios are acceptable, what kinds lend themselves to all the very nice properties of having been in thermal equilibrium in early times, we now actually get to the meat of the matter. We want to know exactly how we can test every single kind of scenario that allows for this annihilation process to be predictive, where dark matter annihilates directly into the stuff that we can observe and that we can manipulate in the laboratory. We want to be able to exploit that as much as possible. And the claim that I'll make is that the most promising avenue towards achieving that goal is to conduct a robust new program of fixed target accelerator searches, so things that aren't normally invoked in the traditional dark matter search program. So, one interesting difference in how we think about the parameter space of direct detection searches, which are more intuitive, more familiar to us, and say accelerator targets, is that in the direct detection parameter space, here in terms of some cross-section, here it's written to be the cross-section for dark matter off of electrons, and there are lots of ideas for how to do that, and some people in this room, including Yoni, have worked on this. But the cross-section here is often the non-relativistic cross-section that you expect to observe with dark matter particles in the halo passing through a detector and giving rise to some sort of energy transfer inside your material of interest. And one thing that immediately strikes you in all of this is that if you take the same couplings and the same parameters that give you thermal freeze-out, and then you translate those couplings into where they live in this cross-section versus mass plane, they end up in very different places because the non-relativistic limit is highly distortive. That in some cases, say in the case of the elastic scalar dark matter candidate, the non-relativistic cross-section for scattering has the same parametric form as the direct detection as the annihilation cross-section and the direct detection cross-section have the same parametric form independently of whether you're considering the relativistic and the non-relativistic limits. But these other ones definitely don't. And the reason is that if your interaction is spin-dependent or if it's velocity-dependent, these things matter a lot when you take the non-relativistic limit. You might, say, lose coherence in your direct detection observable, or you might require a spin flip, or you might require some sort of inelastic transition. These things can be game changers when you're working in the non-relativistic limit, but they only constitute order 1 differences when you're asking what is the cross-section that I need to either produce this in an accelerator, or what cross-section do I need to evaluate whether or not I have enough of a rate for thermal freeze-out in the early universe, because that's still happening when dark matter is quasi-relativistic in early times. And so it makes more sense to define a new variable here, which is proportional to the cross-section, but it's defined to be dimensionless. So in the scenarios that we're considering, we have some y variable on the y-axis, conveniently enough, and it has some epsilon squared in its definition. There's alpha dark, the dark fine structure constant, and a ratio of dark matter mass to the mediator's mass, raised to the 4th power. And when we translate the same models and the same kinds of interactions into the plane of this new y variable plotted against the dark matter mass, then one immediate consequence of this is that the targets are now all within a couple of orders of magnitude of these grayed out existing constraints. So it immediately moves all of the targets for thermal production in the early universe to within a stone's throw of existing experimental bounds. And that's what's very exciting. This is what motivates us to take the next couple of steps to close out what's remaining here. And we get to do this. The reason these are all very similar here is that the kinds of differences between these scenarios aren't very significant when you're working in the relativistic limit. And other things that might be of interest for accelerators as opposed to, say, direct detection is that you have a calculable rate because you're producing dark matter directly. You get to manipulate and tune the properties of whatever instrument gives rise to the flux that you're trying to observe. You're not saddled with astrophysical uncertainties. You know exactly what the velocity distribution is. It's all a delta function at 1. And you know that the thermal targets are now something that you can plausibly shoot for in every one of these scenarios. So one idea that's on the table, the first ever that was proposed and actually carried out, involves hot wiring existing neutrino experiments. So here what we're looking at is the mini-boon experiment. Now the mini-boon experiment at Fermilab is designed to take a proton beam of about 8 GeV, smash it into a beryllium target. That smash produces charged pions, which then decay to give you a flux of neutrinos, and then those neutrinos pass through a bunch of shielding and then scatter inside the mini-boon detector. And it was pointed out by this group here, including Brian Patel, who used to be around, whom I'm sure many of you know, that you could actually get an interesting dark matter result out of this exact same setup, provided that you fire the proton beam away from the beryllium target and directly into the steel of the beam dump itself. This has the advantage of circumventing the decay pipe, which tends to collimate the production of neutrinos, because you focus all the charged pions with a magnet. They then decay to neutrinos, and that's advantageous for you if you want to study neutrino oscillations. But it's extremely harmful if you want to study dark matter scattering. And so what you do is you circumvent that by producing a bunch of pions, including a bunch of neutral pions, inside the steel itself. So here you're not amplifying neutrinos over other exotic things that you're interested in. And then those pions can decay to photons and to other exotica, which then give you dark matter. So in this case, they called it V, but that's the same dark photon that we've been talking about. And then that decays to dark matter, so you actually get a dark matter flux, in addition to a neutrino flux. And then the dark matter can scatter. The dark matter scatters through the same kind of interaction that would be responsible for setting its relic abundance, but the diagram is rotated in the way that we're familiar with. And for nominal luminosities involving 10 to the 20 protons, which is roughly speaking 1 year of operation, and beam energy, which is in the ballpark of 10 GeV, you can take an existing experiment, run it in a slightly funny mode for about a year, and cover some new ground. This, to my knowledge, is the first ever dedicated run that aimed to look for light dark matter below the GeV scale. The only bad news is that if you look at their experimental limit here, that's the Brazil band here, the green and the yellow, it doesn't actually exceed existing limits very much. That it only wins in a very small region of parameter space. But as a proof of concept, this is a promising strategy. It's almost testing some of the thermal targets that are within closest reach. But the problem here is that you're double taxed. You're producing dark matter, and then you pay some very small number penalties, some small mixing penalty squared for the production here, and then you pay that same penalty in the scatter. So you're double taxed, and you have this background of neutrinos that you can't turn off, because this was, after all, an experiment designed to study the properties of neutrinos. And so it'd be bad news if you could just eliminate those entirely. And so a main question here is, how do we improve that situation? Well, one possibility is what Mike alluded to, which is BDX. So this has the creative name of beam dump experiment. And one way of conquering at least one part of this limitation, namely the neutrino background, is that you use an electron beam instead of a proton beam. So here you have an electron beam, a very high intensity beam, at a facility that already exists, say at Jefferson Lab in Virginia. That beam is roughly the same energy as what we saw in the earlier slide with the proton beam. You can actually have a much higher intensity, so you're winning in signal. And then the name of the game is to produce dark matter radiatively, instead of through the decays of unstable particles. This has the advantage of being able to exploit the full energy of the beam, because if I have a particle that's decaying, I can't decay to something that's heavier than the mass of the progenitor particle. And that's independent of how highly energetic my proton beam was. However, in this case, because it's radiative production, it's a continuum process, it doesn't depend on any sort of threshold limitations aside from the beam energy itself. So now you can make dark matter all the way up to 10 GeV in principle. And the way that we do it in our favorite models is that we radiate off a heavy new particle, which then decays to dark matter. That inherits the kinetic energy of the beam. And then inside the detector, depending on which scenario we're considering, you would either expect a scattering signature, where you kick an electron, and that gives you a huge flash of light in the multi-GeV range. Or if it's, say, something more exotic, like a pseudo-Dirac fermion, where there's this mass splitting between nearby particles in the dark sector, the heavier of these, which you can also produce in this interaction, can then decay, and that decay signature can deposit energy. So you're winning by reducing your neutrino background. You're winning because you can have a much higher luminosity with an electron beam if it's operated under the right conditions. but you still suffer the production and the detection penalty. So how well can you do under those circumstances? Well, you can actually do something very interesting. So for nominal projections that BDX, and now the BDX collaboration, which has been formed to study this possibility, has found is that you can actually cover some of the thermal targets, so you're getting a good range of the scalar dark matter model that annihilates directly to standard model particles, and you can start scraping some of the Majorana thermal parameter space. And you could also have a lot of interesting coverage if you're also considering the decay possibility for the pseudo-Dirac case, for the heavier particle decays. So it improves upon what we've seen with proton beams. But really, I mean, because you're double taxed and you pay a small number penalty for both production and detection, even if you made your experiment 10 times bigger, you wouldn't necessarily improve your coverage all that much. So the question remains, how do we get all the way down to this much more interesting region of parameter space? And that gets us to missing momentum. So here, the idea is to scrap the scattering part altogether. Now just focus on the production of dark matter itself and just monitor the beam as it passes through a thin target. So at first glance, this looks very similar to what we just saw, but it's conceptually very different. Here, imagine a single electron passing through first some tagging material which measures its energy. That tells you that you started off with an electron that, say, had 10 GeV of incoming energy. Then it passes through a thin target, a very thin film of maybe tungsten that's a tiny fraction of a radiation length. If something interesting happens as that electron passes through that thin target, say a production event involving first a dark photon, which then decays to pairs of dark matter particles, what ends up happening is that the electron characteristically loses most of its energy. Most of it goes straight into the particles that have been radiated off. And so the telltale signature of dark matter production here is that you had 10 GeV going in, but then as you measure the electron emerging from this thin film with a recoil tracker and with a secondary calorimeter, you find that the outgoing energy is way smaller. You find that it's about 2 GeV or 1 GeV, and critically, you see no further activity inside the calorimeter or any other veto instrument that you place downstream. You're only measuring the electron itself. You're not requiring anything else from the dark matter, which means that the signal is now parametrically enhanced compared to either of the possibilities that we considered on the previous slide. So that's very exciting. Now, the limitation, though, is that unlike what we saw earlier, we're not dealing with 10 to the 20 particles on target or 10 to the 22. We're actually dealing with 10 to the 16. And the logic here is that if you were to suddenly send a whole bunch of electrons through all of this, all at the same time, it'd be very hard to play this game where you're tracking them individually, that you can reliably say that I saw one electron go in with a certain energy and emerge with a different energy. That's what you're trying to identify, and multiplicity and pileup tend to trade off from your ability to be able to distinguish these things. So we want a very low current experiment. So this is perversely something that can only work with a picolamp current. So if you run it for about a year, you get something in the neighborhood of 10 to the 16 electrons delivered to your thin target. But the good news is that if you were to plot the signal kinematics of the outgoing electron for a fixed incoming energy, here we just did a quick little study with a 4 GeV electron beam, which is why this thing peters out around 4 GeV. That's something that you can change depending on your setup. What you find is that if you compare this with other standard model processes that give you the same kind of situation where you radiate off a Bremsstrahlung photon or something more familiar, most of the electrons that emerge on the other side tend to have energies that are peaked much, much closer to the beam energy itself. This is a log plot. And when you're radiating off the signal for different choices of dark photon masses, which are the progenitors of the dark matter flux, you end up with an outgoing electron that actually has much, much less energy than it started with. And so you can tailor your search region to optimize for signal over background in this case. Now, of course, this isn't really a background in the sense that you're actually subject to all of the events that come along for the ride with these standard model processes. You're going to veto all of these things. This is what you would have if you vetoed nothing and just relied on kinematics to distinguish signal from everything else. Ultimately, you do absolutely want to veto everything, but you do have some irreducible backgrounds. And the irreducible ones all involve the conversion of that electron that passes through your target into fully invisible final states. So take, for example, an 8 GeV electron. This is some incoming beam energy. Inside that thin little target where all the action takes place, it scatters an atomic electron. It upscatters it, gives it an asymmetric energy transfer so that this electron recoils with, say, 7 GeV. And then inside that same thin target, it undergoes what we call a charged current quasi-elastic scatter, where an electron finds a proton, and then by exchanging a W boson, it produces a fully invisible final state. You have a neutrino and a neutron, and all of that momentum goes in the forward direction. That looks the same as the dark matter production event. But here, surprisingly, this is completely negligible. And it's worth remembering that on one of the earlier slides, we noted that in order for light-dark matter to be capable of annihilating, to give you the right relic density in the early universe, you needed forces that involved light-new particles. Using the electroweak force, using the weak force of the Standard Model was insufficient because that gave you too small of a cross-section in order to annihilate and get the right abundance. That same logic is on display here because in order to convert this electron and proton into an invisible background for the Standard Model process, you have to pay a penalty of G Fermi squared. That penalty is enough to completely kill processes along these lines for an entire year of running. You might expect one such event. But it's not enough to kill the signal that you're actually interested in, because the signal corresponds to dark matter, visible matter interactions that are actually much stronger than the weak force itself, which is counterintuitive, but it helps you in situations like this. The things you really need to worry about, independently of irreducible backgrounds, you want to worry about undetected visible particles. So you send the electron in, and sometimes it might radiate off an actual Standard Model photon, and then that photon can step through this list of possibilities and produce things which your detector on the other side doesn't observe. There could be a crack in the detector, there could just be some small probability of missing wide-angle emissions of neutrons and other exotica. But the good news is that most of the exotic things which take away the large fraction of the electron's energy are so energetic they're actually very easy to veto. They come along with lots of other charged particles, which is why we have a calorimeter on that other side. And here what we're looking at is the relative rate per incoming electron of various potentially dangerous processes, noting that the irreducible invisible backgrounds are here in the basement, where you expect less than 1 for an ambitious run. So that's the name of the game. Veto everything that deposits any sort of energy on the other side of this target. And there's an experimental collaboration with a white paper that's hot off the presses that is designed to study exactly how this works and execute J-on simulations and come up with a realistic detector concept for exactly what kind of infrastructure you need in order to carry out this ambitious game. The prototype that we have, and this is what ultimately explains why we chose the hexagon for the slide here, is that this is one of the hexagons that constitutes the electromagnetic calorimeter here. So what we're imagining is that you have an electron beam, say one that's provided at Jefferson Lab or at SLAC, or at CERN, depending on whether or not such a beam becomes available. You pass it first through the tagging tracker that measures its incoming energy. This is all immersed in a B field provided for you by the dipole magnet. And then you have your very thin target represented by this little green strip that's vertical. And then a recoil tracker, which measures the outgoing electron, measures its transverse momentum. And finally, the electromagnetic calorimeter, which measures its energy. You have a hadronic calorimeter on the other side of this, which is much bigger than everything else, which serves primarily just to veto other particles. If you made a bunch of neutrons and hadrons, they would induce signals inside of this, and you would know they're not the dark matter signal that you care about. So the eCal is based on work that's been done by CMS in upgrading the LHC for high luminosity running, which is why it's radiation hard. You can fire lots of electrons through it. It's fast. It can handle something like a 50 megahertz repetition rate. And it's highly granular, which means that even if you passed lots of particles through it, you'd be able to distinguish them in very small displacements with respect to one another. The HCAL is an iron scintillator. It's going to be instrumented with readout electronics all the way around, and it's the largest part of this entire setup. And for scale, if you put a person next to one of these, the region that we were looking at is just on the other side of this big blue block that represents the dipole magnet that's surrounding this entire region. The HCAL is the thing that also constitutes a large fraction of the overall cost. But the payoff is what makes us keep pursuing this, because if you now ask what happens to the scalar dark matter candidate that couples to the dark photon, here we have some interaction between the dark photon and to a scalar dark matter particle. If you were to imagine a scattering process off of an electron, this is the kind of diagram that you would consider. If you were to imagine an annihilation process, you would imagine time moving downward where two dark matter particles annihilate each other to produce electrons. This is a model which is CMB safe, so that if you take the non-relativistic expansion of the annihilation rate, you find that it scales as the velocity squared, so it's large enough of a cross-section to give you freeze-out in early times, but it's small so that it doesn't spoil the successful CMB observations. And we have a relic target in this parameter space given to us by this funny variable that's proportional with the annihilation rate. And we notice that this is actually kind of a busy plot. We've got lots of other possibilities here. Namely, we have a bar, which is a B factory, electrons and positrons annihilating, and there's a search for the case where electrons, positrons can annihilate to a photon and a dark photon, which decays invisibly, and therefore it lives in this plane. You also see some interesting direct detection possibilities here, including CREST-2, which set a limit in the GeV and slightly sub-GeV range, and other possibilities for future searches with Super CDMS Snow Lab, and Xenon 10 here, which is based on electron scattering, and the more ambitious Sensei result here, which is a Skipper CCD-based electron recoil semiconductor target that's currently being developed by several groups. And you see LDMX, which is carving out this region that covers the thermal target here. So it seems like it's a very active playing field, and Bell 2 is like an upgraded version of Gabar in Japan. And it's worth noting that if we were considering asymmetric dark matter, so we have the same exact kind of interaction, but for reasons related to physics and very high energy scales, that you have more dark particles than antiparticles as part of the abundance, then you would live above this relic target because you need to annihilate more of the antiparticles away. So that's CMB. So that's why even getting some small fraction above this line is still interesting. But now we could ask, well, what happens if dark matter is a Majorana particle? Now you'll notice that a lot of the direct detection constraints and projections have moved up in the parameter space, because now the same scatter that you might have imagined could give you a direct detection signal is suppressed by velocity squared. And that's related to the fact that a Majorana particle has to interact with a different Lorentz structure, so that when you look at the non-relativistic cross-section, it's punished as a result of that d squared. And you find something similar if you're considering inelastic scenarios. So if it's inelastic, the dark matter is now split between two states, and you have to have enough available kinetic energy to upscatter into the heavier of these. And sometimes that's a prohibitive penalty, depending on what size of the mass splitting there is. But this is safe with regard to CMB observables because the two particles that live inside of this diagram that allows you to scatter are different in the sense that the heavier of these can decay. And if it decays, it's gone by the time that the CMB observables set in, and that means that no annihilation spoils what we've already observed. So we've stepped through the list of different possible dark matter candidates. And for completeness, we'll also mention the pseudo-Dirac case, which has the lowest target in this parameter space, where on account of the inelasticity, you don't have any sort of signatures that don't involve accelerator surges. You'll notice here, everything that we see here is related to an accelerator-based technique, which is related to the power of using relativistic kinematics. We could also ask what would have happened if instead of choosing a dark photon as our representative force to connect dark and visible matter, we had chosen different kinds of currents. This is just to give you an idea of how the parameter space looks if you vary some of the possibilities. Here, instead of a dark photon, you couple to a new vector that couples to baryons and leptons with opposite signs. And a couple of other possibilities, but the take-home message here is that almost independently of what you choose for which dark matter candidate you have and what interaction type you choose, this kind of technique can cover just about all of the thermal targets that might be interesting and that lend themselves to an up or down vote in terms of whether or not they give you a predictive target in this parameter space. So it's also worth noting that independently of any dark matter connection, you could use this experiment to look for long-lived particles. So you have an electron or a muon, depending on which beam particle you want to consider. The same kind of signature takes place, the electron loses most of its energy, produces a long-lived particle as it scatters through this thin target, and then it might produce a long-lived particle which then decays beyond the reach of the electromagnetic calorimeter and inside the H-gal. So this is a more speculative approach, because here you're looking for a signal which is nominally the thing that you would want to veto for the dark matter search. But in principle, this is just to show that the setup that we're proposing has a physics case that goes beyond merely producing dark matter, that it can produce a whole range of other dark sector exotica that we find in the literature. So you can look for just different kinds of gauge forces, you can look for dark photons that decay invisibly independently of their connection to dark matter, for millicharged particles which are produced in that target, and you could look for axion-like particles of various kinds of couplings. So we've stepped through a bunch of different ways of looking at predictive thermal dark matter below the GeV scale. But it's worth stepping back and asking whether I'd like you. So we've stepped through the different choices for what kinds of forces you could have if you're imagining some sort of freeze-out process through some of these diagrams for dark matter below the GeV scale. We've convinced ourselves that scalar forces are ruled out because they also imply very rare and dangerous meson decays, which have excluded the possibility that a direct annihilation like this could be responsible for dark matter's abundance. We've spent a lot of time talking about a dark photon and about its various cousins, which are morally very similar, lend themselves to the same experimental techniques, and have similar predictions for exactly where you live in the y versus m plane that we've been looking at. But there's one possibility that's just a little bit different and involves one of these exotic fifth forces, but it's one that perversely only couples to heavier particles. It's called the gauged L mu minus L tau scenario, where the new particle that we've added, we'll call it a Z prime instead of an A prime, couples only to muons, to taus, and to the various flavors of neutrinos which carry muon and tau number. So what about that? Well, we can do something actually that's very similar to LDMX. We call it muon missing momentum. This is something that Yoni is also involved in. And we put out our paper last year, and the basic idea here is that you could now tell the same sort of story with a muon beam. Muon beams are a little more challenging because the particle you're dealing with is unstable, and you can't make as many muons. But on the other hand, missing momentum, even in the case of electrons, doesn't require that many electrons. You specifically have to go out of your way to have a picoamp current in the electron beam in order to successfully execute this strategy. And so naturally you might wonder whether the limitations in just producing muons in the first place might lend themselves to a favorable surge along these lines. The other nice thing is that now you can actually use a much, much bigger target to compensate for any reduction of actual particle number, because your luminosity is the product of how many particles you send through this multiplied by the thickness of the target itself. And so what that means is that you essentially get the same effective luminosity. So if you can conduct this search using a muon beam, you can have essentially the same kind of reach for models that couple predominantly to muons as you did in the electron beam case with particles that couple to electrons. The main difference in this case, everything else is basically the same except for the beam particle, except that now you can't use the electromagnetic calorimeter to tell you what the energy of the outgoing particle is, because muons don't actually interact very much with matter. They pass through it a lot. That the muon can travel much, much farther through any sort of material than an electron can. And so what that means is that you actually have to immerse everything in a magnetic field so that you can use the curvature of that muon to figure out whether or not it actually went through this target and produced something that you care about, and thereby lost a large fraction of its energy. So that's the name of the game. And we have in mind a two-phase process at Fermilab where we do actually have muons to play with. There's a less ambitious phase 1 where we have 10 to the 10 muons involving the muon test beam facility. And that's something that in principle, provided the beam is acceptable, could be run out of the box because they have space for it in test. Or a more ambitious version which involves the Sequest beamline. The Sequest is another experiment at Fermilab, where we could in principle be able to extract something in the ballpark of 10 to the 13 muons. And the reason we care about these as separate phases is that they have different kinds of physics goals. And so they're represented here. Now we're looking at similar kinds of plots to the ones that we had on the earlier slides, but they're optimized for this model that involves muons. And you'll notice that phase 1 doesn't easily reach these thermal targets. These are sort of different slices of the same parameter space, but they give you some feel. This is the worst case scenario, where you make it as hard for yourself as possible. But phase one can, even with 10 to the 10 muons on target, where you run this thing for only about a month or two, it can cover the slice of this parameter space that's compatible with explaining the muon G-2 anomaly with a particle just like this Z prime. So this is one of the outstanding puzzles in particle physics. And it's something that we could, if it's due to new physics related to particles that interact preferentially with muons, this will be a way of testing that independently of any other consideration. But the more ambitious phase two is designed to be able to cover the thermal targets associated with dark matter directly annihilating into muons, taus, and into their neutrinos. And of course, because annihilation to neutrinos, after neutrinos have already decoupled around CMB temperatures, won't ionize any hydrogen, you don't have to worry about the usual CMB bounds. Those don't apply. So now every possibility is on the table insofar as your choice of dark matter particle is concerned. We don't have to do this song and dance and ask whether each individual case is safe with regard to CMB bounds. So I'll leave it at this and just summarize that we've gone through a little bit of a saga here. That thermal dark matter does a lot of really nice things for us, even if we completely ignore its historical connection, or in the minds of many people, its historical connection with supersymmetry and the Link miracle. But it does a lot of things for us, even if you ignore all of that. That it's a modest proposal and that it's kind of hard to avoid thermalizing if dark matter is anything like visible matter. You have an initial condition which is known to you that requires a minimum interaction rate, which if it annihilates directly into us, you can directly test whether or not this took place. And it's surprising, and it didn't have to be this way, but the viable window that's available for thermal histories is right under our noses. That the part that we haven't actually explored yet is right between the electron mass and the proton mass. And we've done some considerable damage to models above all of this. And the new frontier of trying to explore the other half of this parameter space on a logarithmic scale enables us to consider missing momentum, beam dumps, and something which I unfortunately didn't get a chance to talk about are lots of new ideas for looking at new direct detection targets involving materials that we might not have thought of as direct detection possibilities before. And so the take-home message is that a mature program of searches emphasizing dark matter below the GeV scale can answer some important physical questions about the history of dark matter in some of the most compelling models that have a lot of interesting features. And as part of the process moving forward, we recently finished a panel report for the Department of Energy, giving them a basic research needs assessment about what kinds of small-scale experiments are useful going forward, things that cost less than about $15 million. And if you want to learn more about this, you should absolutely bother Rocky, because he is one of the co-chairs for this process. Yoni and I were also involved, and so we're always happy to chat more, and you can check out some information more with this link. So thank you.
Thank you very much, Gordon. Questions? I'll ask a question. You said these models were compelling.
Yeah.
In 30 words, please explain why these models are compelling. No more than 30, and I'm going to count here.
Okay.
Okay, was one of your words. You have 29. I won't count last.
They give us a predictive account for how the dark matter came to be, and one that we can test in an unambiguous way. I don't know if I'm going over now your 30-word criterion, but it's a no-brainer to me that if there's a simple test for a model that allows us to interact with things that we can manipulate in the laboratory, we should take advantage of that, especially if it's cheap.
Okay, so the compelling is that it's testable.
That it's testable, and it also gives us an idea of where to look. I mean, if we were to see a signal in one of these, that would tell us what next experiment to build. And it's also something that we couldn't really test with any other means. That a thermal origin is one of the few things that doesn't require us to specify what's going on at very high energy scales that we don't know much about. And so that seems like one of the simplest things that we can go after. So I'm willing to say that that's compelling for me.
Okay, good. More questions? Paolo.
Wait for the mic.
So, I mean, one of the arguments that you make is that for some of these models, basically they are not accessible by particle detectors because the cross-section is so low that there is no way. So I think if you find any evidence of new parking at an accelerator, how can you say it's a dark matter?
Well, okay, so
It
this...
solved the problem that much, because I mean, from that plot,
Mhm.
you are in cross-section, never be able to do
Yeah.
that.
So what I would say is that there is no single experiment, and I'm including direct detection in this, which can unambiguously say that the thing that we've discovered in the laboratory is the thing that's responsible for all the evidence that tells us that dark matter is out there. And here's a really simple, perverse example. Let's say you have dark matter, or some component of dark matter, which has a cross-section that's 1,000 times bigger than the thermal relic value. It'll freeze out, it'll only represent 1% of the halo abundance, but it'll scatter in a direct detection experiment with exactly the same rate as something which would have the full abundance, because you've depleted the rate, you've depleted the abundance by a factor of 1,000, but you've increased the cross-section by a factor of 1,000. So these things directly compensate for one another. So in that case, somebody could look at an experiment that does see a positive signal and say, well, you've discovered the 1 in 10,000 fraction of everything that's out there in the halo. Now maybe that's a perverse example, but it would at least demonstrate to me that you would need some other complementary thing before you're fully convinced that you've seen the substance that does all of our structure formation, that leaves an imprint in the CMV. I don't think that's unique to accelerator experiments, but you're absolutely right that if you were to produce something which gave you a signal in any of these experiments, or a collider experiment for that matter, you would have to do a follow-up test, because what you will have discovered is that there's something here which can be invisible and stable on at least the length and time scales appropriate to your experiment. And then you'd have to do something else. And if you could figure out what kinds of interactions it has, then you could ask, what do those interactions imply in the early universe? And maybe that could give you some additional hints if they lend themselves to other searches. But I mean, in that case, if we did see a signal, the obvious follow-up would be to build an experiment that now concentrated all of its direct detection efforts on a particular mass, because that's some information that you could get from an accelerator experiment, because you can control the beam and you can control the detector, so you can at least learn a little bit more about it in that way.
I mean, yeah. Another question?
You can ask a follow-up question.
No, no.
Oh, no, you can ask.
Okay. I think given the hour and that we have a nice reception waiting for all of us, including Gordon, that he's passed the test, he's answered the questions of the old people, and but now we're going to give him the hard questions. And so after we thank him again, let's thank him again. We will invite the non-PhDs to come forward and ask him questions, and treat him nicely and bring him upstairs in a few minutes to enjoy his reception.